So here we have pure data, uh, real-time graphical programming environment for live interactive computer music. You saw I clicked this and the little thing exploded and now it's reading the credits. So it's not just for live interactive computer music, but you can see these little graphical things you can do with it. But there's so much more you can do with it as well. It is a free version of what others use Max as known as Max MSP. Um, in this case, I am going to demonstrate something I figured I could do on here when I was reading the book Elements of Computing. Well, I didn't get to go through the whole book because I got stuck at one point. I said, let me see if I can figure out how to make 8-bit chips and uh, and uh, and not gates and all those kinds of things. Well, at least simulate them in pure data. First, it took me a while to understand it, but here we have the basic everything. I have an example of a memory chip. Here's a 64-bit chip. I made it most 8 bits. In the elements of computing, you're designing a system that's 16-bit, but as we'll soon see, you'll understand why I stopped at 8, and even at 8, it was pretty tedious. So we'll start with the basic. We'll go with the ALU here. So this is the ALU tester window, and here's the ALU. Tiny little words at ALU. I can make it bigger if I wanted to. Um, Let me see here. I I thought I could make it bigger. Maybe not. Yeah, whatever. Maybe not. But I'm gonna open it up. I'm just gonna zoom in. So these are all abstractions that are made up of other pure data windows. So here we have an AND. So the AND is basically this is the atom essentially of pure data. See, we can have relational and logical operators. So this is typical of programming languages. So this is the AND. You get taking a one and another one, and if it tells you if it's going to tell you if it's true or not. So if they both match, they're true. If one of them's false, then it comes out false. Well, in this case, it either gives out a 1 or a 0. So I just encapsulated that. So I didn't really need to create an AND abstraction, but I made it that way so it'd be a little bit easier to understand. So from there we have AND. So now I can call up any AND, and then I created a NOT, and I have ORs and XORs somewhere else. Here's the OR. So it's pretty basic stuff. So here we created the multiplexer. It consists of 2 ANDs, a NOT, and an OR. Right? So it takes in 3 inputs, outputs 1. And then we connect these multiplexers, 8 of them. See how it starts becoming a little bit more tedious with all these connections. You have to do this by hand, clicking and dragging. So I had to stop at 8 at one point, and I couldn't continue building the computer because of limitations of certain things. So the multiplexer here is being used. We have one here. So this is an 8. I labeled it 8 because it's got 8 multiplexers. So this has an 8. I don't know if that's called 8-bit or not. It's not 8-bit because there's no bits in there, so it's not 8-bit. So it's got, this is the 8. This is a not 8, so it's just 8 knots. And then more multiplexers. This is an AND 8, so it's got 8 ANDs. An 8-way OR, so this has 8 ORs, as you can see. And all of these, the reason this is all connected the way it is based on the book Elements of Computing. So this isn't something random. This is how the book tells you the ALU is set up. At least the ALU you're building in that book. So this is the way. It took me a while to figure out how to connect, where to connect everything, and how it would fit in all these things. So it was a kind of a pain to do all this, but I got it to work. So this is the essentially it's the ALU right here. So here it is in tiny little abstraction form. Dec to bin and dec to bin is just decimal to binary, so that I could just type in regular numbers and not have to worry about how many zeros and ones I need to type out. And then obviously bin to dec would be binary to decimal, so now it outputs something I can understand without having to figure out what the ones and zeros mean. So here all the outlets here are going to output your ones or zeros. So those are your decimals. I mean your binary numbers here. So all of those are going to be fed into this and then output the number. So yeah, this is what the conversion looks like. It's basic stuff. I'll continue in a bit. If it lets me here. Alright, so the ALU, we could pick random numbers, it doesn't matter at this point. It has all these little square boxes are toggles, so they either produce 1 or 0. When they're not checked, they're at 0. So negative here is a question mark, 0 here is a question mark, because these last bits, or I guess these would be the most significant bit. I don't remember anymore, but these last bits here output a 1 or a 0 based on whether this answer here is either 0 or negative. So here I have 0x, that's what z means, and 0y. So we turn y into 0, and that outputs 0, and then this comes out. So this will always work. 0x doesn't, it does affect it, see that? So if we 0x and 0y, nothing changes. Okay, so nx means we negate x. So now it's 0 again, but it's not negative. If and y means negate y. So will we get, if this comes out negative, then this should get checked. And look at that. There is your negative. The f does the actual addition, so 10 and 8 are going to give me 18. So this f, if I check that, will give me an 18. And there it is. And I forgot what the NO means, but it works as it's supposed to. So that was that. So the memories here, these memories, I'll use the bigger memory, but as you can see, this is just a 8-bit RAM, and this one's a 64-bit. So you use this one because I made this bigger, so it's better to. But I'm not going to demonstrate the RAM just yet. I'm going to demonstrate the counter because this one's also interesting. Now, everything, the memory and the counter require bits. So let's zoom in to where the bits are. So here's our register. It's an 8-bit register. We zoom in, there's your bits, and there it is, the bit. So here's the problem with the bit, was also a challenge. The bit requires a clock, as you can see here. Now I had to figure out how to simulate a clock in pure data. So it took me a while, but I realized I could just use a metro object. So this metro object, once I turn it on, starts sending a bunch of clicks or bangs, and it's global. So any receive object is going to receive that bang. So essentially, this is me turning on the computer, and then once it starts banging, the bits work like bits. And it took me a while to figure out the way this, how to set this patch up, but I got it working, and it was glorious. So when I click this, now you see these clicks are just kind of fast, but you see it's kind of going the toggles going on and off, on and off. So now the bits are working, and now that means the counter should work. So here's the counter. We have the counter, here's the incrementer, the loader, the incrementer, the loader, and the reset. So what does that mean? It means that when I give it the incrementer a 1, or in this case I toggle it, it should start incrementing. Since it's 8-bit, it's going to go all the way up to 255, then it's going to overflow and go start at the negatives. The loader means whatever number I have here gets loaded onto it. So I have to do it just once and it'll happen. So if I, and the reset will set it back to 0. And the way it works is that it's sequential. So in other words, the reset overrides the load and the incrementer. The load overrides the incrementer, and the incrementer doesn't do anything other than increment. So if I set reset here, you're not going to see it change. But if I do load, you'll see the 14 cent in there. And as long as the load is set to 1, the incrementer doesn't affect it. So you see that? But once I turn off the load, the incrementer should affect it once I turn it on. And there it is. It starts counting up. Reset will always set it back to 0, and it's not going to turn off until I uncheck the reset again. And there it is. It's counting. And now I can move this number. I can set it to 7, load it at 7, and then there you go, 7. I can set it again, 7 again. And I want to go back to 0. I set it to 0, and then there it is. And as long as the incrementer still has a 1, it's going to continue going up, and nothing's going to stop it from counting. That's the program counter. Pretty cool. Anyway, looking back at this code, you'll see the registers. It's 8-bit registers there. So it's got multiplexers, and this one was not that hard to figure out how to connect. It's still kind of a pain, as you can see how big the window is. And it's a pain having to connect all these 8 little things into these tiny little. This one has 16 inlets, so you see that? 16. So that means I have to. It was, like I said, a great pain to do that. See, there it is in the negatives. Anyway, I stopped the incrementer. It should stop. I reset it, set it back to 0, and that's it. That's the incrementer. Let's look at the memory. The memory is pretty ingenious. This little abstraction here or subpatch is just my another, once again, converting. In this case, I'm converting the addresses. These here are the addresses, the memory addresses. So it's converting the addresses so that I can. I forget how I did it, but just know that it works. So this here is the number that will be saved into one of the spaces. This is the loader, so that means 11 is going to be sent to address 1, or whatever this is called, 0. So everyone, you see that's 1. It goes that way. And it goes up to 7. So I need 64, so I need to go all the way. In order to get this one, I have to set all of these to the right. And there it is, 63. Because it starts indexing at 0. So if I put this one down, it'll be minus 7. So that'll be 56, 49, and so on and so on. So I have 64 different places I can save a number. Let me look at the RAM. Yeah, this time I decided to use a bunch of sends and receives because I didn't want to do all that connecting, but I still had to connect a bunch of stuff to the multiplexer 8-way, which is a multiplexer, 2 multiplexer 4-ways, which is just 3 multiplexer 8s, which is just a bunch of multiplexers, which is a bunch of ands, which is just, yeah, you get the point. So all of these are the memory, the addresses, the register. I don't know what it's called anymore. It's been a while since I did any of this stuff. And here are here are the RAMs. Look at that, all the RAMs. See, so all these sends and receives are being received by this guy, and the RAMs are being received by this guy. So here are all the 8-bit RAMs, which gives us our 64. So these are the addresses. So it consists of 8 registers, which consists of 8 bits each. So yeah, it's a lot of work, and it was more work than I would have ever thought, but it was fun, but I don't want to ever do this again. So here, let's do an example. So we have 11. I want to save 11 in memory address number 46. So I set it to load, and there we go. So now let's hope I remember that number, 46. I don't care about the number I saved anymore. 63, we'll save it at the last one. So now we save it. Boom. Okay, so now you see how it sets back to 0, the bottom number. And we can set that to 0 too. So now, I want to access that one again, the first one I saved. Is it in any of these? No. It's in 46. So where's 46? Where here's 42, so 46 is over here. Nope, it's there's 11. There you go. We continue, it goes back to 0. We want to find the last one we saved. There it is, 63. So the memory works just like memory. It's amazing. And it's pure data. And it's all abstractions. And essentially, I understand how computers work, and I never want to ever do this again.